All right, let's just dive right into a concept that is going to completely change how you view calculus, the differential. I mean, if you've spent any time working with derivatives or integrals, you've definitely seen those little dx and dy symbols just kind of floating around. But today, in this explainer, we're going to transform those from confusing mathematical grammar into a tangible, incredibly powerful multi-tool.
So, here's our roadmap for today. We'll unpack the differential, look at the geometry of the tangent, explore real-world error propagation, see why differentials actually win out, reverse the process with indefinite integrals, and finally, tackle the art of substitution.
Kicking things off with Section 1, the differential unpacked, the linear part of the increment.
So the absolutely crucial point here is that dy acts as a linear approximation. It's literally defined by multiplying the derivative of the function, f prime of x, by a really small change in x, which we call dx. Instead of dealing with the complex, messy curve of a function, we're basically just extracting the simple, linear part of how that function changes. It's like finding a straight path through a winding forest.
Which brings us right into Section 2, Geometry of the Tangent, a Visual Anchor. Now this perfectly illustrates the difference. While delta y, the true increment, actually follows the bending, winding path of the curve, our differential dy simply shoots straight up the tangent line. It literally equals the increment of the tangent line's ordinate. By zooming in close enough, we can use that straight line to approximate the curve, and honestly, it saves us from some incredibly tedious calculations.
Moving on to Section 3, Real-World Error Propagation, the calculus problem.
Okay, let's say we measure a cow's hemispherical uter diameter as 26 centimeters, but we have a 0.5 centimeter error margin. We need to know exactly how that tiny linear error propagates into our final volume calculation. Sounds a bit silly, but it's a very real practical issue. Instead of computing a really messy true difference by, say, subtracting the exact volume of a 26 centimeter hemisphere from a 26.5 centimeter one, we just use the differential as an approximation tool. We let our small measurement error be dd. Then, by simply plugging that into our formula, we easily find our propagated volume error, dv. It's fast, it's elegant, and it's surprisingly accurate.
And that leads us to Section 4. Why differentials win? The brute force versus elegance debate.
Now you might be thinking, hey, it seems easier to just plug the maximum and minimum values into our function, right? I mean, why bother with derivatives and differentials at all when we can just calculate those high and low endpoints?
Well, here's why. The differential completely avoids complex, nonlinear endpoint calculations, and it easily rescales if your error margins change without having to recalculate everything. But the real game changer happens when you're dealing with multiple variables. It elegantly allows independent statistical errors, or variance, to add together in quadrature. That means they combine smoothly without making the extremely unlikely assumption that everything goes wrong at the exact same time. This totally avoids the trap of false endpoints in wavy, unpredictable functions.
All right, let's flip the script. Section 5, reversing it, indefinite integrals.
I love this quote because it really captures the essence of the indefinite integral. We're taking the differential, that dx piece we just mastered, and trying to figure out the original function it came from. We're running the machine in reverse. And because differentiating any constant just gives us 0, our answer is always a bit ambiguous, which is exactly why we always have to add that constant c.
Finally, we arrive at Section 6, the art of substitution.
If you look at the messy integral we're tackling here, it is a beast. It might seem completely impossible to just guess the answer. But guess what? Our differential multi-tool is the exact key we need to simplify the whole shebang.
So, we start by targeting the trickiest, messiest part of the function, the 1 plus x squared, and we're going to call it u. Next, we take its differential, which gives us du equals 2x dx. After a really quick rearrangement, we can completely swap out the variables. We're simplifying a complicated problem into a standard, super easy to solve integral from a lookup table.
Just think about how the x dx part seamlessly morphs into 1/2 du. This visual puzzle technique is actually formally known as bringing a function under the differential sign. It is a total game changer. We've literally taken a nightmare equation and reduced it down to a basic power rule, proving just how elegant and powerful variable substitution can be. So, what's the big takeaway from all of this? It's that this single, beautiful geometric concept of the tangent's increment serves as the master key.
It acts as the ultimate bridge for both the practical and the theoretical pillars of calculus. It seamlessly links linear approximations of real-world physical errors straight into the mechanics of complex integration. I want to leave you with this final thought to really ponder. If we can untangle all this complexity, by simply zooming in close enough to find the linear path, what else can we decode? What other seemingly impossible complex systems in our world could be unlocked by simply finding the straight line? Thanks so much for joining me on this explainer, and keep exploring.